My name is Ethan Quinn, and I worked in the Bergbreiter research group this past summer. Here in the Bergbreiter group, we study chemistry with the end goal of discovering sustainable methods of catalysis, novel methods of polymer functionalization, and my research, which focuses on new, greener separation chemistry. This greener separation chemistry can be used to purify water. The most common method of water purification involves filtering water through activated carbon. While activated charcoal is efficient at removing many organic contaminants, it is energy intensive to recycle. In order to recycle activated charcoal, it needs to be heated to over 800 degrees Celsius. A novel and easily recyclable method of water purification is by liquid-liquid extraction using green solvents that are non-toxic, non-volatile, and recyclable. Many problems that typical industrial solvents have are not present with PAOs. PAOs, or polyalpha olefins, are oligomeric hydrocarbons that can be used in place of traditional alkane hydrocarbon solvents. PAOs are alkanes with 20, 30, or more carbons. Traditional solvents that can be directly replaced by PAOs are hexane and heptane. Unlike hexane and heptane, PAOs are non-toxic and considered to be a greener alternative to typical hydrocarbon solvents. One of the most popular traditional alkane solvents are hexanes. Like many other traditional solvents, hexanes are toxic, volatile, and extremely flammable. As you can see, when the flame is held to hexanes, they immediately catch on fire. Unlike hexanes, PAOs are not volatile and do not catch on fire, even when a flame is held directly on them. This is due to their low vapor pressure, meaning that fewer molecules of PAO than hexane are present in the gas phase above the solvent. This inherently decreases flammability. PAOs are an example of a nonpolar solvent. There are no polar bonds within the molecule. Consider oil and water. They are totally immiscible, and no matter how much you try to combine them, interactions between these species are inherently high in energy and unfavorable. PAOs in nonpolar solvents like hexane and heptane are hydrophobic, or afraid of water. PAOs do not leach into polar phases in any appreciable quantity like hexanes do. This means that more efficient and cleaner separations are possible with PAOs than traditional solvents. This implies a high potential for recyclability. PAOs can be used to sequester contaminants from water using a biphasic solvent system. A more familiar example of this is Italian salad dressing. This salad dressing is biphasic and has two immiscible layers that, when shaken, interact with each other to form a highly emulsified layer. PAO in water functions identically, with the nonpolar PAO phase on top and water phase on the bottom. Just like the salad dressing, when the PAO in water system is shaken, it becomes one layer. Both systems separate into two phases when left unagitated. When the two phases are vigorously mixed, the interface area increases, which promotes partitioning of organic contaminants dissolved in water, where they preferentially migrate to the nonpolar PAO phase. Nonpolar contaminants can be removed from water using PAOs alone. Such contaminants include hexane, benzene, dichloromethane, dichloroethane, and dichlorobenzene. Polar contaminants can also be removed from water using PAO solvents. However, a functionalized co-solvent is required to drag the polar contaminants into the PAO phase. In functionalized polyisobutylene oligomers, or PIBs, which are capable of specific interactions such as hydrogen bonding, can be used as co-solvents that increase extraction efficiencies of polar contaminants. When a hydrogen bonding polyisobutylene co-solvent is dissolved in PAO, extraction efficiency of BPA from water increases dramatically. Some of the polar contaminants I focused on removing from water were phenols. One of the phenols is the infamous chemical bisphenol A, which leaches from plastic to water. Other polar contaminants of interest include forever chemicals like perfluorooctanoic acid or PFOA. PFOA is ubiquitous in the environment. Here is a colorful example showing sequestration of a polar dye from water using a co-solvent system of PaO4 and PIB catechol. The PIB catechol acts as a hydrogen bond donor to the dye molecules. This interaction pulls the dye into the nonpolar phase. As previously mentioned, PAOs are easily recyclable. By bubbling nitrogen gas through the PAO phase, the volatile contaminants, such as benzene, hexane, and THF, can be removed. Alternatively, contaminants can be removed via a liquid-liquid extraction with acetonitrile. Recyclable non-toxic solvents, such as PAOs, have many applications and are an exciting branch of green chemistry. I'd like to thank the NSF for supporting the Texas A&M REU program, ExxonMobil for providing PAOs, Chevron, the TPC Group for providing PIBs, Texas A&M University, and especially the Bergbreiter Lab.